Hi, I'd like to devote this lecture to Unix signals. Unix signals are a mechanism that was added to the Unix kernel very early on. It is a uniform mechanism that is used for a variety of purposes that all have in common that the kernel informs a process of some event of interest to it. Now, these events of interest cannot be arbitrarily chosen. They come from a small predefined set. But you will see that signals are a mechanism by which Unix implements a variety of things that start from having a mechanism for terminating processes to having mechanisms that support the kernel's protective function to ensure that processes that somehow misbehave do not affect the rest of the system. So all of these, many different functionalities are all supported by signals. So let's talk about how these signals work. Signals are, because there's only such a small number of them, they are traditionally represented by an integer number. Sometimes when a signal is, we say sent, it is also associated with some additional information optionally. So these events fall into two groups. The book calls one group internally generated events, and the other group is called externally generated events. I'd like to distinguish them by how they encounter or react to signals. So this can be done either synchronous. Okay, so in this case, the signal would be synchronously sent to the process, and this is when it's caused by something that this process just did, hence the term internally generated event. Asynchronous or asynchronously asynchronous notification are not related to what the process currently does, but rather they are related to something that happened externally, maybe a user action, maybe an action by another process. Now, independent of which one of these two types it is, signals provide uniform APIs, and the process to which the signal is sent may then, at its discretion, take one of multiple possible actions. And these actions are either, well, one action is to just ignore the signal. Another one is that the process is terminated, optionally with a core dump, which is a file that contains that process's current memory content. So it can be placed into a debugger and debugged later on. That's called a core dump. But the process may also invoke a user-defined handler, a function that you, the programmer, implements and that is called when a signal is delivered to a process. And then two more functions. Signals are also used for job control purposes. So processes, placing processes into the stopped state and then continuing that process is also done using signals in Unix. And here stopping, remember, stopping means that the process is temporarily suspended until such time when the user continues it with a signal. Now, these signals I mentioned are used for a number of purposes, which I'll describe shortly. I want to point out that the default actions differ for each signal, and usually they perform something that is sensible. So let's take a look at what those signals are and what their default actions are. So first, let's talk about these synchronous conditions or internally generated events. The process does something and typically does something wrong in some way, something doesn't go according to plan. For example, if the process in its executable encounters an illegal instruction, that should not normally happen unless the compiler has a bug, but if that does occur, a signal is sent to the process. Or the process may call the abort function, which is also handled through a special signal. A process that divides by 0 gets the sig-fpe signal, which is a little bit confusing because this is an integer division by 0. A floating point division by 0.0 are not typically represented as signals. It's possible to configure it this way, but by default, IEEE 754 does not do that. Rather, it creates not a number. The signal that you are very familiar with is sig-seg-v, segmentation fault. That's a catch-all signal for all kinds of memory and other privilege violations. I showed, for example, that sig-seg-v is sent when a privileged instruction is attempted to be executed in user mode. The other signal is one broken pipe. If a process tries to write to a pipe where no one is reading from. And there are two more that are related to terminal management, which will become important for developing a job control shell. So those are conditions when a process tries to output something and it is not in the so-called foreground process group of the terminal, and that also leads to the signal being delivered. Now, most of these have a default action, which is to terminate the process, and that's very sensible because it provides a fail stop behavior in the presence of faults, right? And so some of these have the action of stopping the process so that a user can then later take action to continue after the process is placed into the foreground. The process can then be continued so that it can proceed. The second group of events are those the ones that are asynchronous with respect to the running process, right? These externally generated events. Let's look at some of them. So if the user types Control C on the controlling terminal of a process, that results in SIGINT, interrupt signal, delivered to this process. And the default action here is to terminate that process as well. This is how Control C works. Um, if you type on the command line, use the kill command and give the PID, the process ID of a process, then a signal called sigterm is sent. Sigterm is the default signal that's being sent. I will note this is not equal to sigkill. Sigkill is sent when you specify kill -9 and then the PID. The difference between the two is that sigkill can actually not be ignored by the process. It will always lead to termination. So this is the signal that an operator would send if an attempt to kill a process with just kill was not successful. Maybe because the process refused to react to the sigterm signal, but the process does not have the option of not reacting to the sigkill signal. There are signals SIG-alarm. Processes can set alarm clocks or timers, and when those alarm clocks go off, SIG-alarm is being sent. There's a signal called SIG-child that informs a process of a child process terminating. That signal is important for control programs such as job control shells. When you type Control Z instead of C to stop a process temporarily, that is mapped to the SIG T-stop signal. And then it's also possible to kill dash stop a process, and that sends the SIG stop signal, which is different from the SIG T-stop signal, which is sent when Control Z is typed. So the question is who sends some of these signals, right? So some of these are sent actually by the kernel itself. So when you type Control C, then the kernel will recognize that you typed that and send this signal. Others are sent when a user types a command or the command line and wants to send that signal to another process. Notice the terminology here. Kill is it's used because one of the most common uses for signals is to terminate or kill a process. So let's talk about how signals work. So when a signal is so first something has to happen that causes the signal to be sent to the target process, right? And so this could be that this depends on the signal how this works, right? So for example, for the alarm signal, the kernel would set a timer. When it goes off, the kernel would send a signal. I already mentioned keystrokes like Control C and Z, which cause the kernel to send signals, or a SIG-child. That's also something the kernel has to do because the kernel knows when a process exits, right? Because when a process exits, it enters the kernel to tell it that it needs to exit. At this point in time, the kernel has the chance to find out if there is a parent that the SIG-child signal needs to be sent to. But user processes may also send signals to other processes, right? And this happens through a system call called kill that sends these signals. And this can really be done most arbitrarily, but it is subject to some permissions. So, for example, in Unix, you can only send signals to processes that run under the same UID as you do, unless you are the super user. And the kill system call is exactly the system call that is performed by, for example, the kill1 command. So it's an executable in /user/bin, the kill1 command. But many shells, job control shells, also have a kill command built in. And this kill command will use that same kill system call. Actually, as we will see, these job control programs usually use a system call that is related, kill PG, that sends a signal to a group of processes. We'll talk about process groups in a separate video. Also possible to send a signal to yourself. That's called raise the signal, to raising the signal. That's a library function that's provided. So the signal is sent. At this point in time, the signal is set to become pending. Now, it's pending because the target of the signal may be doing something else, right? It may be running on another CPU. It may even be in the blocked state. So after the signal becomes pending, sometime later, okay, usually a short time later, but we'll see exceptions to that, the target process will receive the signal, and then it performs the desired action, right? So that could be to ignore it, terminate the process, or then call a handler for this particular signal. So the details of how this is done are quite complicated. You can imagine that, for example, if a process is running on a CPU, the operating system has to take some measures to inform this process of the signal that was sent to it, for example, by sending an interprocessor interrupt. The operating system has to take special um, precautions or special measures when the target of the signal is currently blocked. In this case, it has to be unblocked. But when, let's say, after a signal handler has been evoked, it has to be put back into the blocked state where it was previously blocked for the same reason. So all these details are quite complicated when you actually implement the kernel. In fact, large parts of the kernel, or at least the logic related to process management and scheduling, are devoted to signals. But here in this class, we're going to focus on those things that are important for programmers using signals. So I want to mention a few of them that, for better or for better or worse, we have to be aware of. So the first one is a pesky issue, which is that signals don't queue. So internally, they are implemented essentially by bits. So for each signal, there is a bit per process, and that bit is either on or off. And this is in the so-called pending mask, which is a small integer word, 32 bits or 64 bits, that says whether a signal is pending. Now, since this is just a bit, um, if a signal is sent twice, that bit switches from 0 to 1 the first time and stays at 1. The bit is reset from 1 to 0 when a signal is handled, so a new signal can be sent. But while a signal is pending, additional events that cause that same signal to be sent will not will not trigger the delivery of two signals to the process. So we say signals do not queue. It is wrong to think of them as messages that could be sent to a process, and then if you send three messages would be received. Now, in this sense, they are more like railway signals, right? So a signal that is turned on, and it stays on until such time when the signal is delivered. When it is reset to off. This is also sometimes called level triggered, like in electronics. So signals don't queue, and this has consequences for a job control shell, in particular if multiple child processes terminate and uh, um, and this triggers a sick child, then if that happens before the first sick child has been processed, no additional sick child is being triggered. And the consequence of this is that the code you write for the sick child handler needs to be prepared to deal with the possibility that multiple children have terminated, but you only saw a single sick child signal. So this is the first issue. The second issue is a more subtle issue. And that second issue is related to the asynchronous control flow that is caused by by having signals or signal handling in your program. Okay, so this has to do with when you actually need to write a signal handler, some code that is being executed when the signal is being delivered to you, and specifically when that happens asynchronously. So asynchronously here means that the regular program that's run, as I'm showing here, the regular program does something, and this external signal, child terminating or whatnot, or the alarm goes off, um, or the user type skill, control C or so on. This can really happen at any point in time. Now, if the reaction to it is to terminate the process, is no big deal. The issue arises when the process wants to handle the signal and then continue in its regular program. So in this case, the signal would, when the signal is delivered, this actually happens with the mode transition. Okay, it goes into the kernel. The kernel then sets everything up, calls back out into user mode, calls that handler, and after the handler returns, it goes back into the kernel, and then the kernel goes back into user mode, transitions back into user mode. And at this point in time here, it continues with exactly where it left off here, right? So this is somewhat similar to a context switch, in that the kernel makes sure that whatever the process was in the middle of doing here, its register state and so on, is the same here. Of course, that is not true if that handler makes some change, right? This handler is actually code that you write, that you provide, that has access to all the processes state. But aside from this, it will continue the process here. Now, the issues arise because of what that handler does or doesn't do. Okay, so I want to show an example here. So imagine you're using the doubly linked list class, and in fact, this code here is from one of our student projects, and you insert something into a doubly linked list, right? So if you recall your doubly linked list, right, you have these list elements in here, and the link pointers are sort of like this, um, and inserting into a list, you have two list elements that are originally like this, and you want to insert a third one, and from here to there. This involves adjusting for pointers. How this is done is shown here on the left, the C code, which on the right compiles to the assembly code on the right. Now, a signal, for example, a sick child, may arrive literally anywhere. So it could arrive, it could, for example, arrive before this instruction, it could arrive after this instruction, this, or it may arrive, outside of list insert, for all we know. Now the trouble arises if it arrives on, if due to some unfortunate coincidence, right in the middle here. Maybe what if it arrives, let's say, right here at this point in time. At this point in time, the list is in a partially completed state. So some of these pointers have been set, but the last pointer has not been set. Last pointer here maybe would be this one here, right? So this would be number 4. This is the one that's being set here. So this pointer has not been set. Now imagine at this point in time, a signal handler function is called, and if that signal handler, for whatever reason, has a need to access that same list that has an element inserted here. So suppose, for example, it would iterate through that list, right? So in this case, it would iterate through that list, but it would not find this element because this pointer here has not been set. So this is just one example where the a function list insert has some state in a partially in an interim state, right? Like here in this case, the state of these list element pointers. And so it is not possible to safely access this data structure until this list insert call has completed. So the signal handler, okay, must avoid situations where it is accessing any state, data structures, variables, what have you, that is being manipulated by the main program that is being interrupted when the signal arrives. Okay, so this main program here, um, this main program here must not manipulate any state that is also accessed here. Okay? So now the question is, how is that done? And there's a larger issue, and this is referred to as async signal safety. Okay, so the async for asynchronous signal safety. The larger question is it safe to manipulate data from a signal handler while that same data is being manipulated? More generally, so this is focused on data that's being manipulated, but uh, more more generally or related, is it safe to call a function from a signal handler while that same function is executing when the signal was delivered? Okay. Um, so, and the answer to this it depends. Now you can make that judgment call for the functions that you write yourself or that are part of code that are part of your program, like list.c, right? You can see that there's a potential for corruption if this function is called from the main program and then also called from the signal handler. But what about other functions that you're using as black boxes, functions that are part of the POSIX API? For those functions, the POSIX standard has defined for every single function whether it is async signal safe or not, and the default is that it is not. In fact, POSIX lists a number of functions, and only those functions are guaranteed to be async signal safe. You can see that list as part of the man page in section 7, signal safety. Um, a funny story, so the book authors in the second edition actually weren't aware of async signal safety, so they provided examples in their books where they would be calling async signal unsafe functions from a signal handler, notably printf. Okay, so printf is not something that you can call from a signal handler if you also call printf from your main program. The reason for this is that printf, while it is executing, it cannot be re-entered because it requires something called the console log, which is something that after that ensures that output to the console is not when it is made by multiple threads is not split into multiple pieces. We'll talk about threads later, but even though our programs so far do not use threads, they still acquire the console log. And if the console log is held and then the signal handler calls printf, it will try to acquire the console log again, and that's not possible. You cannot acquire a log that you already hold. So printf is interestingly not async signal safe. Now, how do we deal with this? There are basically two strategies to write programs that are async signal safe. The first one is to just say, well, let's keep what we're doing in the signal handler very, very minimal. Okay, so just don't call any async signal functions in the signal handler. Okay, do not access any state that is that might be a partially changed state, in a temporarily inconsistent state. Now, if we could fully avoid that, then in many situations there would be no need or use for a signal handler. So in some cases that is exactly required, right? An example is a job control shell, which needs to interact with state that the main program maintains. For example, it needs to record changes in its child processes. When a program that the user has started has exited, then a signal is delivered to the job control program, the shell, and it needs to record that. So in those situations, there is a second option. It is possible to block, we say block, a signal while calling these unsafe functions or while manipulating shared data in the main control flow. So let me show you what that looks like. Okay, so a blocking is also sometimes referred to as masking a signal, tells the operating system that now is not a good time to deliver this signal. Deliver the signal here means to call the signal handler function. And now is not a good time, tells the operating system that even if the signal becomes pending, it should not be delivered until such time when it is unblocked or unmasked. Okay, so this would then lead to the following sequence. Okay, if a process says to block a particular signal here, then if a short time later the event associated with the signal happens, so maybe here, and the signal is sent, then the signal is just marked as pending, but it is not delivered. So there may be some time during which that signal, it has been sent, it's pending, but the receiving process does not react to it. The point in time when the process says calls unblocks this signal or unmasks it, at that point in time, if the signal is pending, then it will be delivered immediately, and the handler will be called, and then everything goes as before. So blocking a signal means to temporarily keep that signal at bay. It doesn't turn the signal off, so the signal still becomes pending, but it will not execute the action associated with this signal. So in this case, in the example of list insert, the responsibility of the main program is to call block signal before the list insert and unblock signal after the list insert, so that there is no way for this signal to be delivered while a call to list insert is in progress. So this raises a number of software engineering issues. Okay, so the question is, well, when should you make use of these block and unblock calls? In what sections of the code, right? Should you protect every single call of list insert with in a block unblock bracket, or should you protect larger sections of the code? A trade-off here is one between safety and latency, right? If you on the one extreme, let's say if your entire program blocks this signal at all times or for large sections of the code, then either the signal would never be delivered, or there may be significant latency, a delay between when that signal was sent and when it was finally delivered. And very often we use these signals to allow a timely response to certain events. So this, on the one hand, we could have large sections of code, right? And on the other hand, we may have small sections of code really only turn it off. But that in turn may, first of all, encounter a fair amount of overhead and also complicate the code. What's done in practice is that typically relatively coarse-grained solutions are chosen. And this would also be my um, recommended implementation strategy for writing a job control shell. So it doesn't need to react to a child terminating immediately. It's okay for there to be some delay, but the delay should not be such that when the shell sits at the prompt waiting for user input, that it would not react to this signal. As a side note, this synchronization pattern, by synchronization pattern here I mean how synchronization happens between a main control flow and an asynchronous control flow that is introduced by a handler that may be invoked at any point in time. It's the same pattern and the same problem that operating systems face when they deal with interrupt handlers. Inside an operating system, a hardware device may trigger an interrupt, cause the invocation of an interrupt handler or interrupt service routine inside the kernel, and when that interrupt service routine accesses any kernel data structures that are also accessed on a code path that the kernel would take, let's say if a user program calls into it, then the same problem arises, and incidentally, the same strategy of temporarily masking interrupts and then later re-enabling them or unmasking them is being used.